Okay, and a good morning to you. Windy, cool morning, but the sun's shining. Okay, Debbie, your justification again for the selection, and give the selection.
Okay, it was Stevie Ray Vaughan singing Crossroads, and I was considering the x-axis and the y-axis as crossroads. And
then she did this to me.
No.
An x and a y-axis. Okay. Crossroads, that's a good way of thinking of an x and y-axis. Okay?
Without the hand signal.
Yes, okay. There have been a couple of questions. One, and I concur that there might have been a little better direction for you on 21. This is something that was brought up earlier. That we have a system here on 21, and it looks like all you're supposed to do is just solve it, and it's like, okay, so what? And then if you turn the page, there's a little bit of dialogue about it in terms of deciding which way would be the best approach to doing the problem. So in that sense, I apologize for the fact that the real nature of the problem was hidden until you turn the page. So it was one of those cases where the editor might have said, turn the page. The next question, I'm going to delay just for a moment. It's number 25, so we'll look at that in a moment. But one of the things I observed in handing back your papers that I gave to you, that there were a number of times where you weren't checking your solutions. I mean, you got your solution, you showed the work, you graphed, but I wanted to again reiterate something I said in passing, and I don't think it was with enough force. When you graph to get your solution, you know that you're in the ballpark, but it depends on the accuracy of your graph. And you really have a need to go back, take the ordered pair, substitute those values for x and y into both equations and see if they work. That's what guarantees you that the ordered pair you found does indeed work. Now another, and this is a minor point, but it's about notation, and I'll just illustrate it in the board. Your solution to a system of linear equations is an ordered pair if it's an independent, consistent system, just a single ordered pair. Now, when we draw an ordered pair, we typically, and I'm just going to use one of them that was a solution for one of your problems, 3, 2. That's the ordered pair. Now, this notation, which many of you used, refers to a set containing two elements, 3 and 2, with no designation as which one's x and which one's y. So this is an appropriate statement for the simultaneous solution. And if you're going to do it this way, you should put in parentheses the 3, 2, and then the set containing that is the solution set. The simultaneous solution would be different than a solution set. So the ordered pair, your solution. If you're going to use the braces, that indicates a set, and that set contains a single ordered pair. Now when you had the dependent system, and I think that's number 27. Is there a number 27 from the homework I just returned? Is that 27? I just returned a set. And I'm thinking that's the one that has the dependent system. Right. Okay, on number 27, then if you're going to talk about the solution set, it is the set of ordered pairs such that y is equal to, and then you have whatever y represented. So I'll just say here f of x for the moment. But that is the way you would indicate the solution set for a dependent system. Or you could argue that there's an infinite number of ordered pairs. And I think it's important to realize that in 27, you had a dependent system. Now, one of the things I noticed yesterday as I was creating the video tutorials for several of the recent lectures, trying to get this idea of a system of linear equations and the idea of classification of a system as dependent, independent, consistent versus inconsistent. It was hard to break that down into separate issues. And I may yet go back and try to do something where I focus on just dependent versus independent, consistent versus inconsistent. So those are some of the concerns from yesterday. One other comment. When you are doing a simplification of a system, such as we are going to illustrate in 25, I'd like to talk about where you check your solution. So we're going to look at 25. I need to get that so it's a little bit better visible. That didn't help me at all. I guess I need to put some weight on the page. See if I can flatten it out that way and see if I can get it there. Let's try that, Debbie. Now this is 25. Now we have a system here in number 25, and I'll write the system on the board. So I have x over 2 minus y over 3, and that's to equal 5 over 6. And the second equation is x over 5, a minus y over 4, and that's to equal 1 over 10. Now this is my original system. The idea to simplify this is to change it to a new system. So I'm going to multiply by the LCD, and again the caution, I'm multiplying both left and right hand side. So let me illustrate that in the next step. I'm taking 6 times x over 2 minus y over 3, and I'm arguing that that is 6 times 5 over 6, that I did the same thing to both sides of the equation. And in doing that, I create 3x minus 2y is equal to 5. Now that's the beginning of my new system. So I have a second equation I need to generate, and in this case 20 is my LCD. So using the same idea, multiplying the left side by 20, I get 4x minus 5y, and that's equal to 2. Now I've rewritten my original system. If I have done my multiplication correctly, the argument is that the original system is equivalent to the new system. Now by equivalent, meaning they have the same solution. When I get done simplifying and get a solution, and I want to check it, I should not check here. I should go back here. Now the reason for that, if I do something careless here, for example, I may just forget to multiply the right side by 6. So I might have some other number here. This new system will not be equivalent. And the solution I find here, and I check at it, may work, even though it doesn't work in the original. So again, caution. When you check solutions, go back to your original. And if it doesn't work there, then you might ask, did you replace the original system with your new one and do the work correctly? Now, at this point, I know there's a question on the problem. Pam, do you want to address your question on the...
Well, I did this and then I solved for x with the first equation, and then I ended up having to get rid of fractions again.
Yeah, the question is, if I solve for one of these, we'll take one of the two equations, and I solve for either x or y, I generate new fractions. Is there a way of getting out of that? And the answer is yes. So let's see how we could get around the problem. And this is going to lead to what we do today. Now this system does not lend itself to substitution. That would be my first point. If I were to go ahead and multiply the first equation now by 4. So I'm going to put out here M4, meaning multiply by 4 all the way through. And multiply this one by 3 all the way through. Now remember how I was talking about trying to get around fractions by doing a substitution that's somewhat clever. This new system is going to be 12x minus 8y equals 20. Then here I'm going to have 12x minus 15y equals 6. So that is yet a new system. And my argument, it should still be equivalent to my original system, meaning same solution, same ordered pair. But now, either one of these two equations I could solve for 12x. So just because this one's right here at the bottom and I'm going to put this right below it, I will just indicate I know that 12x is 15y plus 6. Knowing that, I'm going to bring that in for this, and I have 15y plus 6 minus 8y is equal to 20. And I should have probably pushed everything over a little bit there. This gives me what? 7y is equal to 14, y is equal to 2, and I avoided the fractions. Now once I get there with y equals 2, it doesn't really matter too much where I try to simplify. If I just went back to here because I had this solved for x, then I'd have 12x is equal to 15 times 2 plus 6. That's going to give me a 36. So 12x is 36, x is 3. And I end up with the 3, 2 that I talked about as a solution to another problem. And this just happened to be serendipitous that the solution I talked about earlier is an ordered pair 3, 2 ends up the solution here. So our solutions, simultaneous solution, is the ordered pair 3, 2. Now what I've argued at this point is you should take this 3, 2 and come all the way back to where? To this mess here. So let's see how that checks. I have x, which is 3 over 2, minus y, which is 2, then over a 3, and that should equal 5, 6. Well, this is going to be 9 over 6 minus 4 over 6, and indeed 5 over 6 does work. The second, I had x over 5, so 3 over 5 minus 2 over 4, and that's supposed to equal 1/10. Well, I have 2 over 4, which is, we can just zoom in tight here and just bring that in. This is going to be 1/2, so I need 5/10 there, and if I have a 10 here, that's 6 over 10. So 6 over 10 minus 5 over 10 is to equal 1 over 10, and it works. So my solution does check. This ordered pair substituted into both original equations does work. Now, I'm going to come back to an idea, and then I'll answer more questions. But we are going to make a statement. If I have A equals B and C equals D, where A, B, C, and D represent real numbers. Okay, so I'm assuming that if A, B, C, D are all real numbers, so they're contained in the set of real numbers, and A equals B and C equals D, then the argument we're going to make is A plus C will equal B plus D. Okay. Now I'm going to look at my original system I had, not original, the last one I got. I had this system. Now you understand why I did that, so I can make the substitution nicely. However, for a particular ordered pair, now my assumption is I have some simultaneous simultaneous solution that satisfies both these equations. And that simultaneous solution we're going to call x1, y1. So I'm going to say assume x1 comma y1 is the simultaneous solution. Make that assumption. Then if that's the case, and we, by the way, know what that is. That's 3, 2. If I substitute the x and y for each of these, I just get real numbers, and that's what we just illustrated for our solution. Well, if I just do one more thing here, I'm going to multiply both sides by -1. So I'm going to multiply this second equation by a -1 on the left side and a -1 on the right side. I just changed all the signs. Now I have A equals B, C equals D. So I'm saying add the left side. Variable's gone. Solution. Are you following me or not? I'm having trouble reading expressions. Again, by multiplying both sides by -1 and then adding, using this idea, I eliminate one of the variables. And I end up with an expression, 7 times y equals 14, y equals 2. Then I have to do what? Go back and find x, but that's just by substituting into one of the two equations. So if I come back to this one, 12x minus 8 times 2 equals 20. You can see where my 12x is going to give you 36, and x is 3, and I have my solution. Now I skipped a little bit there because I ran out of space. But the argument again was this gave me 12x equaled 36, and then I just had x equals 3. Now this is a new technique. This is called the addition-subtraction technique. Now I did it strictly as addition. I could have argued that A minus C equals B minus D. Then I could have simply subtracted them and done the same thing. I like the idea of just limiting ourselves to an addition. This particular system should have been done with the addition technique, not substitution. And that's where really getting into that question in 21, where the authors are saying one form of solution was better than another. Solve for y in 21. It works better. And what initially Pam was asking as we started this, and we'll come back now, Debbie, to the left half of the board where I have 3x minus 2y equals 5 on the set, where I simplified in that first step. Thank you. Over here, if you try to solve for x or y here, you create fractions again, and you just got rid of fractions. And I think the question was, are you chasing yourself around in a circle? It just doesn't seem to work. You might have been better off doing what up here? Just solving for y immediately and then substituting.
Well, I thought I was doing too much.
Yes, I understand.
So there's going to be the same amount of steps. I mean, just substituting one for the other.
But you wouldn't want to substitute in the system.
Yeah.
Bottom line, it would work better to immediately go from here to here and subtract. So if you look at the problem from that perspective, you have to ask, what can I multiply times the first equation and the second equation so I could end up with the coefficient of x the same? Then if I'm going to look at it that way, I had to multiply the first one by 24, which isn't the LCD. And the second one by what? 60 in order to make that work. So it's not a nice situation, but if you just use the LCD, and get down to this step, your second system, then it's a lot easier to see what? Going from here. So I would have done this with the addition technique. And that's what the entire next section is about. Taking systems, rewriting them so that you can add or subtract. So I took the problem that was asked and carried it a bit further than the answer merited. But it certainly gives you a better sense of why substitution isn't always the best game to play. Other questions on the homework? Yes? A little bit louder.
23.
23. Okay. Let me slide the book over. And again, let's see what we can do. Oh, I was looking for a monitor we don't have going. Let's try that. Okay, I'm just going to have to get rid of the glare with this. Okay, we'll shade the problem. Now, the 23rd problem is the question. And this one needs to have what done before you ever start? Combine terms, right? So it's sort of a mess at the get-go. So the question, as you look at that problem, you have an option. Before you do any simplification, multiply by the LCD. Then simplify. So in that problem, I would multiply everything in the first equation by 6, and in the second equation, everything by 3 before I did any simplification to avoid the fractions. Oh, hold it. Okay, I'm looking at the first one, and I'm not seeing it very well, and that monitor, it would be 3 in both. I'm sorry, I thought I saw a 2 in the 5 over 3, and yeah, it looks now better up here as a 3. So 3 in both, thank you. I just wasn't able to see the screen on the monitor I'm looking at adequately. So yes, we multiply both of them by 3. But does that answer the first step? Do we still need to go further? Yes or no? You want to go further?
Yeah.
Okay. So multiplying by 3 is a good first step there. If you work with the fractions, you're asking for a difficulty level that's much worse. So simplify first, then combine. Any other questions? Okay, would you be kind enough to pass that set of papers in? Okay, as those come in, I'm going to see if I can get an expression here. And Debbie, I have no idea what, I've been trying to fight both the balance control and the white balance, and I'm not getting much out of this. So let's see what we can get going to the document camp. And it's just the glare is such that if I'm forced to shade things. But here is your statement. If A equals B and C equals D, then the argument in blue, and I'm going to scroll over if I can do that smoothly, and then shade it, you get A plus C is equal to B plus D. And that is a generalization of what we had done on the board. The statement above it, we are familiar with the property, if you have A equals B, then A plus C equals B plus C. But here's a case where you have the two equations and you add them. That's all it's saying. That is the full defense for the method. And what of course is necessary here is something that's stated on page 484. Okay, let's try it, Debbie. Gonna need a little umbrella up here. We want to write everything in standard form. AX plus BY equals C, write everything in standard form. And then the goal, just like we illustrated in the board, multiply each equation by something that will generate the same coefficient for like x. So Debbie, if we go to, hold it. I see you're set up in a different way there. If we think of what we just did with the equation behind me, and maybe if we just zoom out a little bit, yes, where we took this up here, and then we wrote it this way, that's the idea. That's all that's being stated. Standard form for both. Multiply the first equation, left and right side, by something that will make your resulting system have the same coefficients for one of the variables. Now, it's a lot harder to say nearly than it is to show it. Here I did it so the x coefficient is the same. I had a 12 in each. I could have done it so the y coefficients were the same. Just a matter of choice. Once you've done that, if you've written it so one has a negative and the other has a positive, you can add, and you're going to have the variable disappear. You'll end up with one variable in an equation, and you can solve. And that's what we did. So I think if we illustrate that technique a couple more times, it will work. And the question, do you want to add or you want to subtract? I think that's 6 of one, half dozen of the other. I like it as an addition process. The technique is known as elimination because you are eliminating a variable in the process. So whether or not you're comfortable with the language, we'll find out as we look at some of the problems. We have given in example 3, and let's see if that's correct. Example 3, and looking at what we have there, this is on page 486. Okay, let's try that. And again, I think that's reading okay. But in this case, what you have would be a choice of getting rid of x's or y's. And I don't think there's any simple way of saying one's better than the other. So as you look at that on the screen, if I multiply the first by 5 and the second equation by -2, that would immediately give me the x coefficients opposites of each other, and if I add, I'll have a solution. So if I come off there for a moment and show that as an illustration, here is what the system looks like, and you can't even see the blue now. There we go. We would have that for the coefficient of x the same. We add, you eliminate x, you're down to a very simple expression in y, and solve for y. Then, of course, you do have to go back and get x. Now, that's very typical. The alternate approach is shown in the next system down at the bottom, in which you decide to get rid of y. Now, note, I have a plus 3y and a negative 2y as you look at the screen. And if I multiply the first equation by 2 and the second one by 3, just adding immediately gets rid of the y variable. So I'll just scroll up so you can see what's been done. And there is the process. And of course, not everything works out as well as you'd like. We get a rather rotten fraction, 42 over 23. And my guess is your first reaction is you screwed up. When you see something like a 42 over a 23, you're going to look for an error, because that is not going to substitute very nicely. And if you look at it from the standpoint, as we go to the upper part of the next page in 487, notice how the text went ahead at this point and eliminated x to get y. Can you picture substituting 42 over 23 into one of the equations to solve for y? That doesn't work very well either. So I think the best thing is have you practice this. So
plug in that 42 over 23, or the 11, or
yeah, at some point, you can always avoid it.
Yeah, just solve for
yes, you
the
can.
x and do the y.
Yes,
and
you
then
could.
Say, okay, that's it.
Yes, you could.
But yeah,
if you were gutsy. Now, if you want to check to make sure you haven't made a mistake, then yes, you're substituting those in, and that's not going to be pleasant any way it goes. I concur. You can't avoid the fractions forever if you're going to check your work. But you can avoid one of the substitutions by going back and eliminating the other variable. So that's an option you have. Just a comment. When you start these out, because some of these equations you have no idea if you are really going to have parallel lines, the same line, or a unique solution. So when you do this elimination technique, you need to understand that if you have an inconsistent system, you're going to get the nonsense 0 equals 5 or something like that. If you have a dependent system, when you try to eliminate the variable, you're going to get something like 2 equals 2. So when this system results in either an obviously wrong statement or something that's trivially true, then you're going to go ahead and come to the same, well, I say a correct conclusion in the same way that you did it with substitution. We have a lot of problems to do, and I'm thinking of Jennifer's question, or Jessica's question, sorry, Jessica's, on simplifying first. Let's look at page 489 and the 26th problem. Now, is that, well, I just having such a problem getting this to where it reads well without Bloom. And I hope you can see it on the screen for those who are watching the video. I'm having difficulty determining how the video is going across in the encoding. So at any rate, what is your first step in that problem on 26? And I'm going to, let's come off there for just a minute, Debbie. I'm going to try to change the contrast. Now let's see what happens as we go to the screen. Maybe a little bit easier to read, and I'm going to go to the sideboard now. First step, simplify that puppy. Get the first and second equation in the simplest form you can. So this is 26. So I have 2x minus 8y plus 3y. I'm just writing what was written. Plus 2 is equal to 5y plus 16. Then the second one is 8x minus 2y equals 4x plus 28. And just one of the things you really have to be cautious about, that you write down the equation correctly, because my greatest potential for error here is not writing the original problem down and getting every term right. Now I have an advantage because I have a number of people looking at the problem, looking at what I write, and critiquing if I didn't write it correctly. When you're at home on your own, nobody's critiquing it for you, and you can really find yourself with a careless error that you didn't even realize. So if things don't work, first thing to check, did you write the problem down from the book correctly? Now, let's look at what we have here. 2x, that's going to stay by itself. How much of this are you willing to do in your head? You have a negative 8y, a positive 3y, which is going to give you what? A negative 5y, and if I subtract 5y from both sides, I'll have negative 10y. I'm hoping that you're able to do that simplification in your head. This is in standard form now. And then I subtract 2 from both sides, and I will have 14. Now that's a whole lot nicer than the original form of the equation. Standard form. The second equation, much easier to simplify. I will subtract 4x from both sides, and I get what? 4x minus 2y is equal to what? 28. New system. Now, in looking at this, question for you. Which variable is going to be easier to eliminate? You're going to need a smaller multiplier to get rid of x. To that extent, probably easier. A 5 would also work. I can multiply the second equation by 5, or actually a negative 5 because I'd like to add to change my system. So what I'm going to do is multiply the first equation by negative 2. I'm going to put out here multiply negative 2 in a kind of operator notation, multiply by negative 2. In fact, as I look at that, I'll just walk off camera for a moment. That may be more confusing than I like, so let's see if I can state that maybe in a little better way. Let's see if I say m by negative 2. That might be a little bit better without the parentheses. So my new system is negative 4x plus 20y equals negative 28. The original equation, well, I don't even want to say that because I modified it from the original form, but once I simplified, I had 4x minus 2y equals 28. This system is going to be equivalent to the original, meaning it should have the same ordered pair for an answer. This assumes I have a consistent system and it's independent. Now when I add, I get more for my money than I planned. The first variable is eliminated. The negative 28 and the 28 go to 0. So I got a real good payoff here for my effort. I'm at 18y equals 0. So y is equal to 0. Well, if y is equal to 0, and I just think of this equation right here, if y is 0, 4x equals 28, and x is 7. So I have an ordered pair of 7, 0. So my solution to this system is the ordered pair 7, 0. Now, what should I feel an obligation to do? Plug in the 7, 0 into both of these equations to make sure that it works. That isn't going to be the most fun in the world. But let's see what we get. 2 times 7 minus 8 times 0 plus 3 times 0 plus 2 is supposed to equal 5 times 0 plus 16. Boy, do I love that 0. Because that says 14 plus 2 equals 16, and it does. But the only thing that made that tolerable was what? A 0. Anything else, and it wouldn't have been so nice. What about the second equation? 8 times x, so that's 8 times 7, minus 2 times 0 equals 4 times 7 plus 28, 56 on the left, 28 plus 28 on the right, 56 for both sides, and it checks. Yes. You know, Michelle's saying, just be pleased. You don't have a bunch of fractions involved. Think of what happens if you had fractions in the original and a fraction involved in the solution. You would be up a little bit longer checking this one than you would with what we just illustrated here. Okay, let's come back to the set. Just looking at what we had in the document, Cam, all three of those you'd approach the same way, correct? And it's certainly not a case where as you look at those, you're going to have a feeling that one technique is better than another. I think it's very clear as you look at 26, you wouldn't want to do it by substitution right out of the gate. So if we think of what we did in our first step, let's come back now to that sideboard and that system. Note on the screen, second system. You could have divided by 2 and had x minus 5y equals 7 and substituted immediately and had a nice solution by substitution. There's certainly nothing to say that addition is the best here. Once I made that first adjustment, it lent itself to substitution. We've had three different forms of solution. I started to say 3 systems, but we've had 3 different forms of solution. My guess is that graphing is the one that you would least do to find an accurate answer. Addition, subtraction is sort of the guarantee. You do addition, subtraction, elimination, and it always is going to work. Substitution works sometimes as a quicker and more advantageous approach, but not always. Let's see if we can find anything more interesting. Michelle.
I don't want to use this term because I know it's wrong, but when you, up at the front board, when you multiply the top 3x by 4 and the bottom 4x by 3, that's sort of like an LCD, right? It's
in a way.
Sort of, because this one did the same. The LCD was 4, and you multiplied the top one to get to plus. So the 2x.
Yeah, no, wait a minute. Okay, I'm going to make a distinction here, and I understand what you're getting at. On the sideboard again, as we look at that system, we multiplied by a -2 to get a -4, so that we would have the coefficient of x opposite of each other. That isn't an LCD at that point.
No, but to get that where you multiply by -2, I mean, even if it was just a 2, I mean, I know it would be different, but...
I understand. Okay, I get the point. Now...
Because what I did to solve that problem...
You've got a good argument.
Started, I just multiplied the bottom by 2x and got 8. You know, I did the 2 and the 4
okay.
by each other.
So you made them an 8 in each case.
Right.
And I see what Michelle's getting at, and I was not thinking of it in terms of a denominator. How about least common multiple? A multiple is the right idea, but you are correct. What is the least common multiple of 2 and 4?
4.
4. If they were denominators, you'd say the LCD is 4. And that's a good argument. That what you're trying to do is to get them the same coefficient, and so yes, you are correct. And I should have perhaps tried to explain it that way, because the LCD idea is precisely what you're wanting. You want these two coefficients to be the same, just like when you add fractions, you want the denominators to be the same. So if we cut back to the front board, Debbie, to where we have the 3x and the 4x in that first system, what Michelle was noting is that the LCD of 3 and 4 would be what? If they were denominators. You'd have a 12. So this 3 and this 4, if they were denominators, you would try to get 12. Okay, as a multiple.
Right.
The least common multiple of 3 and 4 is 12, and you're right on target. That should be the approach that you're facing. So you want to know, what can I change those to? And if you think of an LCM, just like they were denominators, a good point, well stated. Let's see if we can find a problem to illustrate that, and I think not necessarily going to worst or best case, but this happens to be on page 490. This is a problem in 33 where you're supposed to be making some assessment, but just looking at the system I have up on the screen. And let's take now the approach that Michelle was thinking. I have a 1/3 and a 1/6, so what could I do? So we come back to the system. I could make that first one 2/6, right? And then the bottom is 1/6, so if I multiply the bottom one by 2, and I had 2/6 for the top one, then I could go ahead and subtract. What would you prefer to do? Get rid of the fractions. So there, and we get back to this question that Pam brings up. You know, you may be chasing yourself a little bit, because the first thing in that system is multiply the first equation, I think, by 6 as we look at it one more time. We multiply everything in the first one by 6, everything in the bottom equation by 6. And then we'd be in a position to go ahead and find an LCM. Now, as you look at that, there may be other approaches. So as we come off there, it says one student solved that system by multiplying both equations by 6 to clear fractions, and another student multiplied by 12. Assuming they do their work correctly, should they both get the same answer? Well, if you're going to multiply both sides by the same number, yeah, you get an equivalent system. That's not going to change it. Let's go back and look at that again. If I multiply by 12, okay, the first equation by 6, it's argued, and then I guess we did what? Multiply by 12. I guess both of them were multiplied by the same number. Yeah, it'll work. What's the disadvantage of using a larger number than you need? Just get bigger coefficients, but it'll still work. If we look at that one, and let's go to that again, Debbie, and I'm going to write that up on the board, and let's see how we'd approach that. And my first inclination is to try to do that with the smallest multiplier I can use. So I have the first equation. I'm just writing the second one now. And that's equal to 0. I love that 0. Okay, because that 0 is going to make life a little bit nicer. But I'm going to trade this system in for what? A new system. So I'll write it just below it. We don't have fractions in the new system. So I multiplied this entire equation, left and right side, by the same number, which is going to be 6. So I have 2x minus 3y is equal to 42. The second one I multiply by 6, and I get x plus 2y is equal to 0. And I think you can see how getting rid of the denominators, life looks a lot easier. Now, what might you be inclined, even though we're supposed to use the addition technique here, you might be inclined just to solve for x right here and substitute it in. That would be one approach. We are supposed to be practicing the elimination technique, so what would you now do? Multiply the bottom one by -2? If you can get by just with one multiplication, you're better off. Now, I could have technically multiplied the top one by 2, the bottom one by 3, but then I'm doing twice as much work. So I think it's better to multiply the bottom one by -2, and when I do that, I'm going to get a new system. So my new system coming up here is going to be 2x minus 3y is equal to the 42. And then I have negative 2x, negative 4y equals 0. Then when I add, you can appreciate the author's approach. What's nice about this? Yeah, you get something that works, right? I mean, I hope you appreciate the care that's going into these problems so you don't get things like 42 over 23 very often. So here we'd have y is equal to -6. Now, given that, I would probably take this y at -6 and come right down here into that bottom equation where I had x plus 2 times y is equal to 0, so that says x is -12. So my solution is -12, -6. Now, the only complication here, I have what? Both parts of the ordered pair negative. And that is going to make it a little more awkward to go back up here and substitute. But is there any question in that one? Yeah, Pam.
How did you get -12? Because you have 2 times -6
Well, it's
is
because I
-12.
didn't
And carry it
bring
over.
the -12 to the right side. It's a good point, because I have what? X minus 12, and I kept the -12 in my head. I should have added a 12 to both sides and get positive 12. So it's 12 and -6. So it's not as bad. We only have one negative. And I would have found very quickly again with a -12 that it didn't what? Check with one of my equations. So one of the things I am going to ask, and I'll try to make the assignment consistent with that, I would like you to substitute your ordered pair into the original system to make sure that it is satisfying the conditions in your original system. Okay, if we go back to the document, Cam, I think we can see that problem again. And LCD's probably the best. And then I'm reminded of a comment, Perry, when we were talking about signs and how easy it is to mess up a sign. And I just illustrated how easy it is to lose a sign, and the only way of catching yourself, go back, substitute in, and see if it is correct. Now, we've been working in some of the harder problems. If we come back to the earlier ones, there's some gifts here. So let's talk about Christmas time. Okay, I'm looking at 5 and 8. Do you see why I say Christmas time? Nothing has to be done with number 5. 2x equals 8, x equals 4, and you're done without even working. Number 8, if you add again, things just fall out Christmas time again. So the early ones aren't so bad. Let's go off there and over to number 13. Now 13 is nearly a gift, because what can you do in 13? Multiply the first equation by 2. I wouldn't try to eliminate the x. I would only try to eliminate the y, because it is so much clearer that it's better to multiply by one number than both equations. Coming off that, I saw one that caught my eye. Okay, this one, in number 14. Which is your better approach? Multiply by 3 or multiply by negative 2? Give me an argument. You're going to change the first equation in number 14. I'm arguing you can multiply the first by negative 2, or you can multiply it by 3. Which would be your better?
3.
Okay, I've heard both answers. I've heard it both as being better. I would choose 3. Reason? You make fewer mistakes multiplying by a positive than you do a negative. So you'd have 3x plus 3y. Your x's would go out. You'd have 5y, and that might be a better result. In some of the problems, it's very clear what you want to do. In others, not so clear. Let's look at 22. At this point, no clear choice. I can't think of a particular reason for why I want to multiply the top one by 5 and the bottom one by 4 as opposed to what? 3 and 2. What's your only argument for the 2-3 combination? Smaller numbers, less likely to make a multiplication error. There is not necessarily one best way to do each problem. So if you were doing your work, and let's look at this one more time. Let's say that I'm writing my solution and I multiplied the first equation by 5, the second one by 4. Michelle says to me, hey, I multiplied my first one by 2 and my second one by 3. We started different, but what should be true at the end? We should have the same answer. So when you start comparing with each other and say, what did you do? You may disagree in approach, but you should have the same ordered pair. If you don't, then you've done either a multiplication that had a small error in it, you changed a sign like I did a moment ago, some little piece that got messed up. But I would like you to check your solutions. So we're going to start with number 5, and we're going to go through number 42. However, we're going to limit ourselves to every other odd. How do you like that one? Every other odd. So you're going to 5, then you'll not do 7, but you will go to 9. Okay. So in a sense, you're taking 5x plus 4. 5x plus 4. Would that work? Well, I'm not sure. If we take 5x plus 4 and x is 1, then you'd have 5. Oh, I'd have to take, starting with x equals 0. Well, that's still not going to do it because that would not work. So I'd have to go 5 plus, then 5 times 1 plus 4. 5 times 2 plus 4. Nope, that's not going to work either.
I think every other odd is going to work.
Yep, I was trying to give you a nice equation. 5, 9, 13. We're skipping 11, then 5, 9, 13, then 17, and so on. You get the idea? Check your answers, though. I will try, as I write this on the web page, to give a nice equation for it. I just can't come up with one in my head quickly enough. So with that, Debbie, what did you select from this potpourri on the CD you have?
Actually, I have to agree with you. Today's algebra was fun. So
Well, very good.
I thought tonight's homework would be easy, so I chose Cheryl Crow, Run Baby Run.
Okay. Run, baby, run with Cheryl Crow. Have a great day.